Okay, well, some properties now of jointly discrete random variables first has to do with independence. So remember we said already before we even defined variables jointly, we said x, y are independent if the probability x is little x, y is little y is equal to the product of those probabilities separately for any x, y that you wish to choose. So, and the way you would show they're dependent is find a single pair of numbers, little x, little y, where this doesn't hold. Well, we can just use our notation now. So this is the same as P, the joint PMF has to equal the product of the marginal PMFs for all. Okay, so that's the same thing. Okay, so they will be independent if that's true. Now, we have if x, y are independent, then the covariance of x, y must be 0. Okay, this is very useful, as we will see. So, proof, suppose let x, y be independent. Okay, then covariance x, y. Use whatever one you want. Let's say e x, y minus e x, e y. Right? But e x, y is equal to over x over little y, little x, little y. Okay, from the proposition about the expected value of g of x. But this is equal to sum over x, sum over y, x, px of x, y, py of x, and this is from the independence. This breaks apart, right? This breaks apart into this piece and this piece, which I grouped this way. But this can just be brought outside of this sum here. So I get the marginals, right? E, x, e, y. That's the proof. Okay, it's also true, converse is not true. It's also true that there are examples where the two variables are dependent and yet the covariance is 0. So converse not true. A good example here is also given in the textbook. You could have something like this, say minus 1, 0, 1, 0, 1. Say this is y up here and this is x over here. All right, well, clearly x and y are dependent. Why? Probability, let's say, there you go. There you go, 0, 0. Probability they're both 0 is 0. But that's not equal to px0, py0, which is equal to x is 0, 2/3, y is 0, 1/3. So x and y are dependent, yet the covariance xy equals e minus ex, ey, and we have ex is equal to 1/3, ey is equal to 0, and exy, the product, is equal to 0, 0, 0, right? One is always 0, so this is 0. So the covariance xy equals 0. Okay, yep. All right, certainly true. Okay, now we have to get into some properties of covariance, which will be very helpful going forward for the rest of the course. So we have 4, they're easy too. So 1, covariance xy equals covariance yx. This is obvious from the definition. 2, covariance xx. This is just equal to E of x minus E of x, x minus E of x, which is E x minus EX squared. So this is just the variance of x. 3, covariance of AX. This is just that doesn't make any sense. Covariance of AXY is equal to E. Okay, so I have AX minus E AX and Y minus EY. The A can come all the way out here. So this is just equal to A covariance XY. If I put this together with 2, we have that the variance of AX equals covariance AX, which is equal to A covariance of X, AX. If I use 1, I really want to be cute. AX, X, I get A squared covariance X with X, A squared variance of X. Okay, now the next one is for sums. The covariance of, let's say, I equals 1 to n, xi and y, j equals 1 to m, is just given by all pairs. Okay, and this isn't terribly hard to do. Let me just make sure I have enough time. Yep, okay, so it should not be hard. All right, well, let's just run the definition really. So this is equal to I need this minus its mean, right? Expected value of this minus the mean of that. The mean of that I can bring the E inside, so I get 1 to n. And this now minus the mean, I can bring the mean inside. Okay, and now I can, since the sum is the same, I can say this is E. It's the same sum here, right? So sum right? And we're there. We're done, I think, pretty much, right? The E can come all the way inside of everything For one thing, these are constant with respect to this index. These are separate indices, so I can do the whole thing all at once. So I get E over the double sum. And I just have an nm size sum here, right? N times m terms. And I'm taking the expected value of that. We know the expected value of sum is the sum of the expected values. So I have I equal 1n, j equal 1m, e of the whole thing. But what is e of this? It's just the covariance of xi, y, j. So that's your result there. That's very useful. So you just can match up pairs like that in a double sum. For example, suppose we had 4 variables like let x, y, w, and z be our v's, then covariance, remember covariance is only pairs, but I could have pairs like this where I add them, and then I know this is just equal to covariance of xw plus covariance yw plus covariance xz plus covariance yz from property 4. That's what it tells you. All right. Yeah, I think it's too risky. I got to go to the next video.